Hi everyone. Today we'll be talking about reaction rates, and actually the term of chemistry, or the theme of chemistry that we're doing right now, is called kinetics. So it's the rate of a reaction, and don't always assume that faster is better. Okay, sometimes we want to slow a reaction down so we can pace ourselves. When we're talking about reaction rates, the main theory that we're thinking about is this thing called collision theory. And the premise behind collision theory is that we need, so if I write down our basic chemical formula, let's just use that for an example. A plus B, A reacts with B to produce C and D. We need reactants A and B to collide. And not only do we need them to collide, we need them to collide in the proper orientation. And what that means is, so if we were to sit there and say, and here's my classic example, and you know I'm not an artist, so I know some of you may have done something like this in biology, but we need A and B to collide in the proper orientation, because we need their active sites to fit properly. Okay, so in a situation like this would work. However, if my A and my B were to go like this, that would not be an effective collision. That wouldn't be a collision with proper orientation. So we're going to go to that. So take home message, when we're trying to describe collision theory, we need our reactants to collide. They need to collide with proper orientation. And now, not only do they need to collide with proper orientation, they need to come together with enough force or enough kinetic energy, so enough speed and force to break the bonds of A and B to make new bonds. Okay, so it's not just like a little touch. They need to come together, so A and B need to be hurling or colliding together with enough force to break old bonds and make new bonds. Okay? And I'm just going to turn off my fan because it's annoying to me. One moment, please. Okay. So, number one, A and B need to collide. Number two, they need to collide with enough force to break old bonds and break new bonds. That's what leads to an effective collision, and that's what leads to products being formed. Now, if you don't have an effective collision, your rate is going to be zero because you're never going to make anything. But since we're talking about kinetics and how the rate or how fast a reaction occurs, we're assuming an effective collision, right? We're assuming that A plus B comes together in the right way to make C plus D. So now we're talking about how fast do those products get formed. So the rate of our reaction depends on how many times A plus B collide and how many of those collisions are effective, meaning how many of those collisions are successful in making your products. So an increase in the number of effective collisions leads to a higher reaction rate. So I've already talked about orientation. I did my little diagram up there, but that's one of the major things we need to talk about. Some orientations for collisions between molecules or ions can lead to reactions, while others can't. We're going to talk about the successful ones as being effective collisions. So those effective collisions are the ones that have the right orientation and enough energy to break old bonds and make new bonds. We also have these unfortunate collisions that, yes, they're colliding, but they're not successful. Okay, so we didn't make C or D. They rebound, and they're really unchanged. So A and B stay the same. Okay, so the rate of reaction, and here's a nice little mathematical formula for us, depends on the frequency of collisions and the fraction of those collisions that happen that are actually effective. All right, so let's look at some mathematiques, shall we? All right, so consider a system where the collision frequency of 1,000 collisions per second And the fraction of effective collisions is 1 out of 100. Okay. Bing, I'm going to put a little 1 there. That's a 1. All right. The other 99 rebound. No reaction happens, so we will call those ineffective collisions. So for our purposes, our reactions per second equal 1,000 collisions per 1 second times 1 effective reaction, so 1 reaction per 100 collisions. And once we cancel out like terms, that gives me 10 reactions per second. Okay, so that is how we incorporate this equation. Okay, all right, so then let's take a look at what happens if the collision frequency is increased to 5,000 collisions per second. So we're increasing our odds. And I always like to use the example like, a guy wants to go on a date on a Saturday night. If he only asks one girl and she says no, guess what? He's not going on a date. But if he asks 500 girls, somebody might say yes. Okay? So if you increase your frequency, you may have more success. However, you can increase your frequency, but you've got to have also effective collisions, right? So let's take a look at this math. So if my reactions per second, so we're going to look at my rate because this is your rate, reactions per second, we will do 5,000 collisions for 1 second. That happens. Now we'll do our effectiveness, and it's still 1 reaction per 100 collisions. So we're 1% effective. When we do that mathematique, okay, that gives me 50 reactions per second. And that's our rate, right? My rate is 50 reactions per second. So therefore, the increased frequency in collision contributes to an increased rate overall when we're comparing A and B because my percent of effective collisions is the same. Okay, it's like 1%. Got it? Okay. So lastly, what happens if the fraction of effective collisions is increased? So this is different. Okay, so now I'm talking about this part of the equation, right? Let's go back to our original situation where I have my rate, which is my reactions per second, right? And we'll go back to the situation in A where I have 1,000 collisions per second, and I multiply that by 1 reaction over 20 collisions, so we've got way more efficacy happening here. Okay, and whammo whammo, this brings me to 50 reactions per second. So you can affect your rate in one of 2 ways. You either up the frequency or you up the efficacy, the efficiency. Okay, more effective collisions. All right, so my conclusion here is exactly what I just said, actually. Increasing collision frequency or fraction of effective collisions will increase your rate. And if you increase both the collision frequency and the fraction of effective collisions, you're going to, I won't say exponentially, but you'll definitely increase the rate to a greater degree. Okay, so when we take a look at the factors affecting rate and collision theory, okay, there's several that we talk about, and I'm sure we've talked about it before, and even in biology you do, but I'm going to go through it yet again. All right, so like I said before, here is our equation for the rate of reaction. the collision frequency multiplied by the fractions of effective collisions. All right. So when I talk about collision frequency, what factors affect how often A and B are going to collide? Well, these three: concentration, surface area, and temperature. And we're going to talk about how each of those affects everything. Okay. The second one, the fraction of effective collisions, is affected by the nature of the reactant. So when we talk about the nature of the reactant, we're saying, what is it like? Is it a solid, liquid, or a gas? Does it have an active site? Does it make an ion? Things of that nature. So that's what nature of the reactant is. What are the characteristics, the chemical characteristics of that reactant? Okay. Catalysts. And what we know about catalysts are that they are things that typically bring your reactants together, but they are not consumed in the reaction. And lastly, temperature. And the thing you're going to see is that temperature is kind of the gold standard here, because temperature affects both the number of collisions as well as it increases the effectivity of those collisions. Okay? All right. So if we change the nature of the reactants, so I'm on this point right here, if we change the nature of the reactants or we use a catalyst, that will change the size of an activation energy barrier, making it easier or more difficult for those molecules to react. So what we're going to do is we are going to look at a little chart here. And like I said, if you've taken bio, you have seen this graph before. All right, so let's just take a look. Shall we? All right. So moving on up. So looking here, activation energy. Activation energy is the energy that's required for my reactants to, for each of the reactants to possess in order for the reaction to be successful. So first off, what did we say had to happen? We said that for an effective collision to occur, my reactants have to be in the proper orientation. Okay, so that's one thing. But not only that, they have to collide with enough force to break old bonds and make new bonds. Okay, so the force or the energy required to break old and make new is what we refer to as our activation energy. Okay, and the variable is E subscript little a. All right, so my activation energy serves two purposes, like I just said. It overcomes the electrostatic forces between colliding entities. So first off, you know how when electrons get too close together, they will repel. So the activation energy overcomes the innate repulsion between two different molecules, right? And that activation energy is also the force or the energy that is there to weaken the bonds of the reactants so they can be broken. Because remember, we got to break the old, make the new. All right. So let's take a look at this little graph here. All right. So we have potential energy on the y-axis, time on the x-axis. Potential energy, don't forget, is found within bonds. Okay, and we talked about this in earlier lessons. So potential energy, you've got your reactants here in A, so reactant, and you've got your products here in B. Okay, so when we're looking at our reactants just sitting there, nothing's happening, they're just sitting around doing their thing, they're perfectly stable. If we want to change them, though, and break old bonds, then we need to have a certain amount of energy. We need to add energy. We're not adding potential energy because those are found within bonds. They're stable, they're happy, it's sitting. So we need to add some kind of kinetic energy that increases the energy of your molecule. Okay? And then if my molecule has an increased amount of kinetic energy, we know kinetic energy is the energy of movement. We can affect that kinetic energy with temperature, Okay, and so like I said before, our A and B, our reactants, need to hurl towards each other with a certain amount of force. And that force is to break old bonds, right? So if there is enough energy to reach this hump here, and they are hurling towards each other with enough energy to break those old bonds, then they are capable of making new ones, meaning they are capable of making new products. If, however, they don't have enough energy and they can't, like, so a situation like this, and they can't go over this hump, guess what? They're back down in reactantville. All right? They're staying as they were. So that's exactly what I'm saying here. In a chemical reaction, the potential energy is the energy stored within the bonds, and the kinetic energy is the movement of the particle, with like the bond movement as well as the particle movement. Okay? So once again, the only way you're going to make a product is if your reactants have enough energy to break their own bonds. So they're breaking the old bonds. Okay, and that energy is called activation energy. When we refer to an activation energy barrier, it's like the minimum amount of energy for a reaction to happen. Think of it like a cutoff for a university. You need 85% to get into this program. That is your activation energy barrier. If you've got 84.3, guess what? You're not getting in, right? So there's that. So that's our situation with activation energy. So let's take a look at this reaction. Okay, so we have a reaction here where we are bringing two reactants together, hydrogen gas and iodine. Okay, they're coming together and they're forming a new product. Now, looking at this, my delta H is positive 53 kilojoules per mole. So since it's positive, we know it's an endothermic reaction. Right? So we need to put energy into the system in order for that reaction to take place, which kind of makes sense. So take a look here. Here are my reactants. Here's my H, so that's my H2, right? And my I, bing, 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 bing. Okay, so those are my two reactants. They're sitting there minding their own business. They're stable. That potential energy is within these bonds here. Okay, the minute we start adding energy, we're adding kinetic energy. So you can do that by agitation. You can do that by increasing the heat. You are adding kinetic energy to your system, which is what you need to do because it's endothermic, right? So the system's absorbing energy. And so now your system has absorbed enough energy to reach the top of this complex. And this complex here is when we start, and I'll do this, and I'll do this. Do you see how I switched them from horizontal to vertical? Because then, I'm going to pick a different color. Hold up. Okay. And then we're going to start breaking old bonds and making new bonds. Do you see what I just did? So we're breaking the old bonds in purple between the hydrogen atoms and between the iodine atoms, and we're making new. Now this is transition, transitory, right? Nothing's set in stone yet, okay? And this is what we see right at the top of the activated complex. And another word for activated complex, also known as the transition state. Okay, so this is where, and it is exactly what it means. It's a transition state. You're transitioning from hydrogen gas and iodine to hydrogen iodide. Okay, so you are here. But when you're here, you haven't committed. It can still go this way or this way, right? You need to have enough activation energy to go over the hump. Okay, so our final potential energy in an endothermic reaction, because this is where we end up with HI and another HI, all right? In an endothermic reaction, these products have more energy. Why? Because they had to absorb energy for the reaction to occur, right? More energy was required to break old bonds, okay, and then make the new ones. So these guys have more residual energy, all right? And this is an important part right here. Here's my net potential energy change. As you can see, if we do products minus reactants, it's a positive number, a positive delta H, which means it's endothermic, right? This thing's positive right here. Okay, so along the flat region to the left, the molecules are moving towards each other, and that's what I've got here. So this is just a step-by-step. So this is step 1, right? As the molecules approach, they're affected by repulsive forces and begin to slow down. So this is what our activation energy overcomes, because they're originally repelled by each other, but guess what? That kinetic energy overcomes that repulsion. That activation energy overcomes that repulsion. So then we're at this stage of the game, 2, where we make this activated complex, like this transitory thing that I said before. It's unstable because really it's not stable because nothing's really been made or broken. We're kind of in like a halfway zone, okay? No man's land. And so then you got your partially broken and your partially formed bonds. And at this stage of the game, because they're like everything's just halfway done, it has the most energy associated with it. Okay, and we call it the transition state because it can't stay like that forever. You got to pick a side. You're either going back down to number 1 or you're going to move to number 3 where the products are made. Okay, so when you've formed your activation complex, like I said before, your reaction can go forward or backwards. But if there's enough energy to form the new bonds and break the old bonds for good, like permanently, then it'll go forward to make our product. Okay? And like I said before, the energy difference between the reactants and products is the enthalpy change. And I'm just going to swing it back down, which is right here. Okay? The difference between products and reactants. Okay? I've already explained why it's an endothermic reaction, because my products have more energy than my reactants did, and my delta H is positive. Okay, now we're going to do the opposite type of reaction, an exothermic reaction. Okay, and so let's take a boo on this one. So here's example 2. So if you take a look, we've got 2 reactants, carbon monoxide and nitrogen dioxide, and we're making 2 new products, so we know a chemical reaction has occurred. We also know that my delta H is negative 227 kilojoules. All right. So the fact of the matter is the enthalpy change is negative. So because I know it's negative, I know it's an exothermic reaction. And the way we're going to draw one of these bad boys are, so here are my reactants. So I've got carbon monoxide plus nitrogen dioxide. So those are my reactants. Here are my products, carbon dioxide plus nitrogen monoxide. All right. And so let's just take a look here. Once again, y-axis is my potential energy between the bonds. My reaction progress, same thing. This is from reactants to products. That's all it means. Reaction progress just means as you go from reactants to not from to production. Hold up. Okay, so it's just moving along from left side of the arrow to the right side of the arrow. Okay, so once again, we're going to take a look. It's the exact same thing. We still need to put a little bit of energy into our reaction because these guys are perfectly happy being what they are. So you do need to put a little bit of activation energy to encourage the breaking of old bonds and the making of new bonds. But what you're going to see is that this hump right here is way smaller than an endothermic reaction. Okay, so once again, you're going to have your activated complex on top of that curve. So that's the intermediate, the intermediate chemical where it's halfway between breaking old bonds and making new bonds. Nothing is permanent, nothing is made. It's just you're in between. Okay, and once again, now in this case, remember what an exothermic reaction is. It's where energy is actually released, and that is why our products have much lower potential energy, because energy was released in the system, or to the system, to the surroundings from the system. And for that reason, my products have less energy. That describes this shape of the curve. Okay, and when you take a look, my delta H, products minus reactants, since my products have much less energy, potential energy, my delta H is going to be negative. Okay, so there's that, and that's exactly what's explained right here. So when I said to you the gold standard was temperature, because temperature not only increases the frequency of collision, but it also increases the percent of efficient collisions. It does both. So a lot of times, if we want to increase the rate of a reaction, we heat it up. Okay, and if you take a look here, experimental evidence has shown that a small increase in temperature seems to have a large effect on a reaction rate for those two reasons, because it does both frequency and percent of effective collisions. Okay, frequency, now if you think about it, why is there more frequency of collisions? Well, you heat things up. According to the kinetic molecular theory, the hotter something is, the faster the molecules move. The faster the molecules move, just by chance, you're going to have more collisions in like a beaker or a test tube or wherever you're doing your chemical reaction, right? So you heat it up, they're going to collide more often. Not only that, but if you heat things up, they're moving faster, so they're colliding with more force. Get it? That's the beauty of temperature. Chemical nature of the reactants I've kind of already talked about, but let's just revisit it. It's what the reactants' chemical features are. So how strong are the bonds holding them together? How many bonds are there? Okay, are there multiple bonds? So those, because don't forget, you've got to break the old bonds. So what you're breaking is very important, and that's what is considered a chemical nature. All right, and that's what the second point's saying. Fewer bonds react faster and larger, or than larger numbers of bonds, because it makes sense. If you have to like break up 2 bonds versus 20, obviously, it gets a little more black. It's a little more gray than the black and white I'm showing you, but usually fewer bonds is easier to break than more bonds. Okay. Secondly, the size and shape of the molecule or ion can also affect reaction rate, because depending on how easy it is to get in and break those bonds. Okay, so those are our chemical reactant or chemical nature of the reactants. The fifth one, concentration and surface area. If we take a look, don't forget what concentration means. Concentration means the number of moles. So concentration is moles per volume, or the number of entities or amount of entities per volume of solution. Right? So if you have more reactants available to you, the more there is, the more opportunity for collision. Get it? Same thing with surface area. Say I have this big honking block of A. We can attack A this many ways. Okay, so imagine these are reactant B's colliding, right? Versus, say I have the same amount of A divvied up like this, right? Those are little A's there, and then I can still get, look at all this, and it's the same amount. We use this example all the time. For instance, like it's quicker to cook ground beef than it is a steak. Or if you want more flavor from a coffee bean, you grind it finer, okay? So that kind of thing. So you just have more opportunities of collision if you A, have a greater concentration of your reactants, or B, more surface area of your reactants, because you're just increasing opportunity. It's back to a guy asking 1 girl out on a date versus 500 girls out on a date. That's not to say those are effective collisions, actually effective date asking opportunities. You guys know what I'm saying, but that's a whole other conversation that we're not going to have right now. Lastly, I hope you guys still appreciate my jokes, by the way. Lastly, catalyst theory. So let's take a look and let's remind ourselves what a catalyst is. Okay? And if you are a biology person, you may, that moved. Enzymes are biological catalysts. So remember, what is a catalyst? And catalyst is some kind of chemical or enzyme that allows for more reactions to occur without being consumed in the reaction itself. Okay? So let's look right here. For any reaction to occur, the kinetic energy of colliding reactant entities must be equal to or greater than the activation energy. So what that means is my reactants need to have enough energy to go over that hump, right? If they don't have enough energy to go over that hump in our chart, they will just move on back and they'll stay as reactants, right? Now, here's the thing. Catalysts do not increase frequency, all right? They don't increase the frequency of collisions, but what they do is increase the efficacy. So there's more efficient collisions or effective collisions, all right? So the way they do it is they provide an alternate pathway for the reaction that has a lower activation energy. Okay, so if you take a look here, this is one chart, but what I'm also going to do is remember back to my Pac-Man thing. Okay, what a catalyst might do. So here's my A, here's my B. My catalyst might be a structural catalyst that actually brings A and B together. Whoops, I don't know why it keeps doing that. Sorry, guys. It brings A and B together in the proper orientation. So we're not going to have those situations where B is flipped the wrong way or A is flipped the wrong way, right? So a catalyst will bring our things together and make my A and B collide in the right way. Okay, so that's called a structural catalyst. So once again, increasing the effective collisions. Another way a catalyst works is it reduces the activation energy required for A and B to go over that hump. Okay, so let's take a look here. Here's my reactants, and in blue, this is a catalyzed pathway. And as you can see, and I don't like the fact that that keeps moving, see how much lower the energy requirement is for a pathway that has a catalyst involved versus uncatalyzed. So the reality is naturally happening, a greater percentage of my molecules are going to be able to overcome this hump versus this one. Okay? Now, those are the factors that affect chemical reactions and the rates of those reactions. I still want you to read section 6.3. I'd like you to answer the questions found on page 72. And I will talk to you fairly soon because there is another lesson, 6.6. As usual, ask us questions either on the discussion tool or through email through the LMS feature. Take care. We'll talk to you guys soon. Have a good day. Bye.